Alrighty, so hi, I'm Gabriel Hesch. I am one of the co-hosts of the Breaking Math podcast. Together with Alex Alanis, we've created a brand new show called Turing Rabbit Holes to discuss points of view of physicists and mathematicians and scientists like Alan Turing, hence the name Turing Rabbit Holes. These guys, or rather, Alan Turing built early computers to crack the Nazi Enigma code. We want to talk about their ideas and their philosophies and possible applications of those ideas to today's world. We will also, of course, be discussing modern scientists, and we'll quote them. We're going to talk about government policy. We're going to talk about challenges that we face as a human species today and tomorrow. We will also be taking some deep dives into math and physics and machine learning and artificial intelligence and bringing it all together into this idea of what it means to be a human in this day and age. Is that a good way of putting it? What do you think?
Yes, it is.
Excellent. All right, Alex, want to tell us a little bit about yourself and your background and how I rope you into doing this podcast?
This was just a great idea because I've developed lots of step-by-step materials for mathematicians and physicists, so this is a natural extension of that. So I have a PhD in physics, which I got back in 2000 in particle physics, University of Houston, and since then I've done a lot of interesting things in physics. I did a postdoc at Los Alamos as an experimental physicist at that point, a gigantic accelerator facility where you have two perpendicular X-ray machines the size of football fields that would take pictures of imploding pits to make sure that we do what they call stockpile stewardship, which was to assure the President of the United States that, yes, our weapons still work. And that is part of the verification of physics. That was very interesting to see how good we can capture the inside of something that's pretty complicated as it gets imploded. After that postdoc, I ended up being back in theory at the Nuclear Weapons Design Division as a nuclear weapons design physicist. And that was interesting because I had to learn things about high explosives and how materials get driven by high explosives and all sorts of phenomenology of shock waves. And of course, as things get compressed, the nuclear physics begins to kick in, and then it gets hot from a radioactive point of view, a lot of gamma rays and protons and energetic charged particles, and it gets pretty interesting as you go from nuclear to a thermonuclear process. The complexity actually begins to simplify because it begins to look like the inside of a star. What I found interesting was that Los Alamos and the other National Nuclear Laboratory, Lawrence Livermore, put together about 1,000 shots in the history. And so we have a lot of data, and we have a lot of facilities like the DART facility I worked at. And you get to the point where you take theoretical physics and experimental data, and you have to chop it into computer codes. You have to make approximations. And even with even with arbitrarily large computers, and I was working with some pretty big ones, you begin to think that the idea of the movie The Matrix might not be sensible because no matter how big the computers are and how good our data is, we'd only get about 90% of the results to match.
Wow, that's a lot there. That's a lot. So if I may insert something here, I worked with Alex for about a year and a half at a company here in Albuquerque, New Mexico, a DoD company. And we would have these conversations during our lunch, just go off on physics and physicists and all these things. And I love these conversations. I absolutely love them. I love hearing from physicists who have been working in the field for so many years and have experienced these things. I'm fairly new in my career, so the ability to capture these conversations on a podcast format is something that really excites me. That's the reason why I actually originally started my first podcast, the Breaking Math podcast. And now I got to do something very, very similar with somebody who has been doing physics longer than I've been alive, probably. Again, we're not going to talk ages here, but that's probably approximately true.
Correct, yeah.
So yeah, one thing I'd like to do with this podcast is everything we do in these episodes, when we go on a deep dive tangent, we have papers. I say we. Alex has written papers. He's shown me that we're going to publish on the website they completely outline the episode. Not only that, they also include diagrams. They also include equations. They just deep dive right into it. So if you're listening to an episode and you really like it and you want to get more information, you can go to the podcast website, which will, again, full disclosure, that name is still, I haven't secured the domain name yet. It'll be a Turing Rabbit Holes podcast website. It very well may be turingrabbitholespodcast.com. We'll see. I actually heard that you're not supposed to include the name podcast in your name. That's supposed to be uncouth now. I thought it was helpful. Turing Rabbit Holes podcast. Sure. I don't know. Who knows? Maybe we'll buck that tradition. I don't know yet. Anyways, these podcasts are rooted in papers that Alex has written. So all of that information is there, including the one that we're going to do today as well. So yeah, you'll find that on the website. One more thing I'd like to say, during the recording of this first episode, we actually did 2 videos. If you'd like to hear about 2 of Alex's favorite books that have really solidified his view of physics and been very instrumental in his understanding of the standard model of physics, check out the other video. It's just, I'll call it Alex's favorite books, or I might include your last name if that name is already taken. Alex Alanese's favorite books, Turing Rabbit Hole's favorite books. So it's a great little video, so it's definitely worth checking out. I'm very excited about this podcast, and by the way, who is this for? This is for anybody who likes to hear scientists talk shop, basically. Heavy focus on the standard model of physics, but also artificial intelligence, where we're going as a humanity, the limits of mathematics and physics. Are there limits? Is there a chance that physics might be dead? We're going to talk about all that stuff. And more. Also, please send us your comments. You can comment on these videos. You can also email us at turingrabbithole@gmail.com. That's TuringRabbithol. Do I have to spell it out for you guys, really? Turing like Alan Turing, not touring like you're going to tour France or something like that. So we'd love to hear from you as well. I'd love to hear your thoughts, and if you have questions for Alex, please send them our way. So without further ado, let's see. What more would you like to do with this podcast and with physics education in general?
Well, I'm interested in creating a finishing course for 4-year degrees and for masters and PhDs in physics and math too, showing that mathematics and physics, unlike medicine, really is a unified subject, and it can be done in a semester to show, cover the fiber bundle formulation, which is a very concise formulation of both geometric theories like general relativity and the standard model, which has internal symmetries, and how that basically codifies how we think new physics might exist. Say extensions of the standard model to group SU5 or SO10, theories of string theories that may or may not actually turn out to be true. So just the idea, once in your life, you see that physics can be codified compactly, concisely, and then you can go off and be an experimentalist or a theorist in some nook and cranny. That's fine, but you should see, and people always say that physics is too specialized now, and I don't believe that.
Interesting. Wow. So I'm curious if I'm sure you aren't the only one who's thought of this idea of like a finishing course or something, or something like that. However, of course, you have done a lot of legwork in terms of reading books and writing papers.
Yes.
So that's really cool. And the idea with this finishing course is, in essence, it might save a lot of time of people who haven't really been exposed to as much the relationships within math and physics, and have seen the trends on where discoveries have happened, right?
Right. And some of the work I did, I looked at the work in developing a wave equation back in 1834 that anticipated Schrodinger's wave equation in 1926. Absent that, you're fine if you have a PhD in physics, but knowing that and knowing the history of that, I think gives you a much more solid understanding of both quantum mechanics and classical physics.
Nice. So with that in mind, perhaps we should go ahead and talk about what we're going to talk about on today's episode and the paper. So Alex wrote a paper that was originally, you emailed it to me, 70-some pages, and you whittled it down?
Yes.
Okay. We've it's no longer 70 pages. Alex has edit it down to 47 pages.
Yeah.
Right. And the paper is about near misses in the history of physics and math where, do you want to summarize it?
It was just looking back at the 19th century and looking at the notion that space-time may be curved, that atoms have complex structures like vortex atoms. Near misses in that sense.
Yeah, I'll go ahead and pull the paper up now. The paper you'll see on the website is called Mathematical and Physics Limits for Mortals and Immortals. Why did you put the mortals and immortals piece in that?
Because no matter how arbitrarily advanced you get, there are still limits that you will not be able to grapple with.
That's philosophically and perhaps theologically speaking, that's pretty insane.
Mm-hmm.
There will always be limits. It's in the nature of mathematics.
Yes.
That's crazy. Things like Gödel's incompleteness theorem and things like that. So now, before we get into this paper, I want to just talk about the titles in the table of contents. They're intense. So the paper is split into sections. The first section is called Near Misses and Blunders in the History of Physics from Limitations Imposed by Ignorance. And that's where we just talk about people who were ignorant about certain things and they just missed key things that were right under their nose at the time. So that includes some parts of, you said wave mechanics in 1834, or Kelvin in the age of the Earth, or things that were just completely wrong, like vortex atoms or knots, which were popular in the 1850s. We'll talk about those, and even string theory to a degree. But then we get into a topic. Check out this title here. This section is called The First Death of Mathematics. Fourier, Cauchy, Dirichlet. How do you say that? Dirichlet. Hey, I was right. Dirichlet. Riemann, Henkel, Cantor, Hilbert, Gödel, and Turing. On my other podcast, we had a reviewer give us a 1-star and say that I mispronounced Gödel. I was saying Gödel, full disclosure. But even Richard Feynman mispronounced the names of mathematicians, so it's okay. But I learned Gödel or something like that. Anyways, and Turing, the first death of mathematics. That sounds horrible. Like the death of mathematics. Wow, yes. It's such a powerful thing. The next parts of the paper get into the second death of mathematics. Now, what's the difference between the first death and the second death?
So the first death of mathematics was I'll say Gödel theorem. It's an incompleteness theorem, and it has an equivalence in computer science. In computer science, Alan Turing. The version of that is, and you've all experienced this probably, a computer is really a logical system operating logically on ones and zeros, and sometimes it stops. And you don't know how long you have to wait before it comes back and you don't lose your precious work, or you finally give up and turn off your computer. It is the recognition that there are certain theorems that act like that there are logical systems that you don't know how long it's going to take. So the fact that infinite time is likely is what makes mathematics incomplete. And it's a little more complicated than that. There's some things that we know to be true, but we know that the proof would take an infinite number of steps. So in that sense, math cannot be completed.
Wow, that's deep. What about the second death?
That happened 20, 30 years after, in the 1960s. It is showing that you can't even build consistent systems of mathematics. That the way you choose your fundamental axioms don't guarantee eventually a future inconsistent result.
Wow.
So you can't even trust the consistency of mathematics.
Oh my goodness. Wow. Okay. Ooh. Wow. That's deep. So as you guys can see, this just dives deep right into it right from the onset of our very first episode. Just to give you a little preview here, we even have a third and even more deaths of mathematics. Mm-hmm. You have something here called The End of Insight by Stephen Strogatz. What was that one about? Little preview?
That one was about, Stephen Strogatz is a mathematician. He was, and as you'll see in the paper, he was worried that as we rely on proofs by computer, we have lost our intuition. I mean, there was a famous theorem that was solved in the 70s by computer called the four-color theorem, which means that you need only 4 colors to color any arbitrary map such that no two countries share the same color. The proof involves so many computations that no human will ever understand that. So he has an interesting take that science will become autocratic, that we'll just have to take it on faith that the machine proved it correctly, and that we've lost our insight that way.
That's a little scary, isn't it? A little scary. I mean, do you think maybe if Elon Musk is on to something with his Neuralink idea about enhancing the human brain?
No, I don't think that Steven Strogatz is correct on that one.
Okay.
And there's another program called Chematica, which solves all organic chemistry problems. But that one you can take to the lab and verify. So I don't think we're losing insight. I think we're getting shortcuts.
Okay. Oh, wow. Cool. Yay, optimism. I like your optimism. That's great. Cool. And then as the paper goes on, you talked about the end of physics reductionism, then even more deaths. Man, you just got a mathematical graveyard here,
yes,
just like everywhere. All these, these pillars of mathematics in their graves. Yeah. Man, Morris Klein, is math created or discovered? What an interesting topic there. This, of course, we won't get to today. It'll be on a future podcast, so you'll have to, you'll have to tune in for those, and you have other ideas. Euclid was not even wrong. What I've heard that phrase, "not even wrong," before.
Right. It's Wolfgang Pauli, and it was an insulting way to say you're not even wrong. Yeah.
Wow. It's an insult to those who were wrong. Wow. Goodness. Oh, man. And then that's not even half of the paper. But, as the paper goes on, you've got all kinds of discussions about mathematics, including who even cares about death, carry on with life. Again, it's the ever optimist, which is great. Practical limitations. Goodness, I'm just scrolling. I could just keep going and going here. Anything else you want to mention?
Then it eventually leaves the depths of mathematics and moves over into the realm of physics and looks at the limits of physics, whether it's classical or quantum mechanical. There are also lots of limitations in these structures on top of the mathematics.
Yeah. Ooh. Oh my goodness. Oh, and you get the Shannon's information theory and limits of codes of information transmission. Mm-hmm. Okay, so we talk a lot about Shannon's information theory in the Breaking Math podcast. That's a huge implication. So I see you touch it on here as well. Yes. We just talked about another episode about communicating, with language and Shannon's information theory and encoding information into human language. Mm-hmm. Like even that's an aspect, or even human memories. If you really want to have a trippy conversation, think about how your brain encodes information into your memories, and that is limited by Shannon's information theory. You can never do it perfectly. So what you're experiencing, it's not really quite reality. So anyways, not to freak anybody out, but it's true. So. Okay, and then you just keep going on and on, and then the end here, you talk about tools for amazingly compact codification of current and potential new physics. We get into calculus of variation, internal symmetries of the standard model, starting with circles. Circles are fun. Symmetries from geometry or space-time and fiber bundles. My goodness, that's fun with fiber bundles. Goodness. And then you get into ER equals EPR, tensor networks, and even the holographic principle and the multiverse theory. Does anything truly ever end in foundational physics? And then a warning to the American physics graduate student. That's at the very, very end. Goodness.
Yes, I did.
Little preview on the warning.
It turns out that in China, you go through a physics boot camp. They collect physics qualifying exams from our good schools, and they publish together books, and they sit there for 2 or 3 years working these problems. And they're essentially master's level or PhD level students when they come and compete against brand new American graduate students. And so they actually publish the books, and I cite them in this paper. You can go get them. They are large collections of solved PhD qualifying problems, so that you at least know what you're up against.
Wow, that's insane. Goodness. Wow, the Chinese are really that's some solid preparation. Wow, I guess, since they're, I guess any country that wants to be a leader in a field, obviously that's pretty consistent with what they want to do. And then finally, the last section here is math and physics has mostly a history of blood, sweat, and tears. So,
indeed.
Goodness. Okay. Yeah. So without further ado, let's go ahead and get into the first section in this paper on today's podcast. This will all be about the very first section. We'll see how far we get, and then we'll, the next, we will soon publish the following episodes and get through the rest of the paper. So this entire paper starts off with, as we said earlier, the section called "Near Misses and Blunders in the History of Physics from Limitations Simply Imposed by Ignorance."
Right.
So. Yeah.
So the first one is interesting. The Greeks were anticipating atoms. Not a bad thing, given how much they didn't know.
Yeah.
After that, we move forward to the 19th century when mathematicians began to discover other geometries, the hyperbolic geometries and spherical geometries. And so they naturally looked at around the stars and they asked themselves, is there a way we can use measuring methods to detect deviations from Euclidean space? Not enough. The idea that space-time may be curved came to mathematicians in the 1850s when they were discovering non-Euclidean geometries.
Okay. Yeah.
And to the limits of experimental astronomy, they couldn't find any deviation.
Okay.
So they anticipated the ideas of Einstein by 70 years roughly.
Yeah, interesting. Yeah, and they missed it. So one interesting question that I've heard addressed many times is, let's say Einstein was never published. Einstein never came around. Let's just say that his parents never met in some parallel universe. Would we know what we know today if he never published his ideas? In fact, there's an idea that was that I first heard from the physicist Michio Kaku, and he was talking about that with what we now know, if Einstein had never came around, that we would still know about general relativity from other mathematics that have proven it.
Right.
So that's kind of interesting. So yeah, but you got all these stories of these near misses, and in fact, wasn't there a story about the orbital of Mercury?
Well, that would have been the evidence that there was already a known perturbation in the orbit of Mercury that people were explaining in several different ways. You could make the sun an oblate object instead of a perfect sphere, and that would explain some of the discrepancy of the orbit of Mercury. There's also the chance that there was another planet, they called it Vulcan, that might have explained the perturbation of Mercury's orbit. They never found Vulcan, and the oblateness of the sun was not enough to correct the missing details. So if they had used that, if they had built a theory of general relativity in the 1850s based on that data, they could have anticipated Einstein by 70 years.
Interesting. Wow. Yeah, and then of course the bending of space and time as predicted by or explained by general relativity perfectly explains the orbit of Mercury.
Right.
So interesting. Now, of course, that's not the only time that there was a near miss. History is full of them, and that's why you wrote this paper.
Correct.
So what were some of the other interesting ones?
So in 1834, Hamilton developed something called the Hamilton-Jacobi wave equation, which was essentially the same as Schrodinger's wave equation. That's 1834 versus 1926. The problem there is that theory was way ahead of itself. There was no experimental reason to take the limit as the waves became geometric rays, and so just back to classical mechanics. I suppose, thinking about it, maybe they were aware of spectra of atoms, and so there was something quantized in their awareness, but they didn't connect the dots. So it took a lot more experimental evidence. For instance, to run electrons through crystals showed that electrons have a wave behavior. They have diffraction through a grating, and so it took the data of the 1910s and 20s to finally get people to realize that a wave mechanics approach is the correct way.
Interesting. So now, as an electrical engineer, I read all about Hamilton and Jacobi, and I used their work in my linear algebra classes and in all sorts of my classes. But I'm curious, for somebody who's never heard of the Hamilton-Jacobi equation, let's say that you've got an art student who has an interest in physics and watches physics videos on YouTube, how would you explain both the what and the why of the Hamilton-Jacobi equation?
So it turns out that Newton's law, F equals ma, can be rephrased for different approaches to solve different problems. It can be phrased in Lagrangian formulation, in which you sum together the kinetic and potential energy, operate on it, and derive Newton's law, F equals ma, the differential equations. There's a Hamilton form, there's a Hamilton-Jacobi form, there are many other forms, Poisson bracket forms, and each has their purpose and approach, and many of them led to different approaches to quantum mechanics, Heisenberg's matrix mechanics from Poisson brackets. So it's just F equals ma in various guises.
Interesting. So then, again, when this Hamilton-Jacobi equation was written, this was far before Max Planck first published his idea about the Planck length. So far before anything with quantum mechanics whatsoever.
Except possibly the spectra of atoms.
That's right. Yeah.
But it wasn't enough to...
Yeah, they brush against it and they missed. So
Right.
they missed it there. But yeah, that's crazy. And again, you have other blunders that go back even with Lord Kelvin. He had some very, very strong opinions about the age of the Earth. It's interesting here. There are many instances in the history of science where you've got a very arrogant physicist trying to tell, a chemist or a geologist or a biologist the way it is, and they're so Why are physicists stereotypically so cocky?
I think that's on TV.
Okay, that might be a TV thing. I got that a little bit when I read some Feynman books. Like they're like, it all boils down to physics. Your field just boils down to physics when you think about it, But still, they think that gives them authority to talk about certain other fields. Lord Kelvin is one of those physicists who are too arrogant.
He got into a large debate with the geologists of his time. The geologists were pretty convinced that the Earth had to be at least 1 billion years old, given erosion processes, if not more than 1 billion years old. Lord Kelvin basically started the Earth off as a lump of molten mass and said, okay, to cool down to where we are today took about 500 million years. Or I think it was 500 million years, but so there's no way the Earth is 1 billion years old or more than 1 billion years old. So that was a pretty big blunder because he was not aware of radioactivity, and considerable amount of the Earth's heat is from radioactive decay.
Yep. Interesting. So completely wrong. Again, he, not to say his math wasn't wrong, just again, he didn't account for radioactivity.
Had no notion of it, right?
So again, that's a blunder from ignorance and arrogance both. So, wow.
So the next one reminds me of string theory today. It's called the theory of vortex atoms, and it was 4 Scotsmen, James Clerk Maxwell, Professor Tate. For now, I'll stick with them. James Clerk Maxwell developed his theory of electromagnetism, and it finally showed that there had to be a connection between electromagnetic movement and radiation of the creation of light. And they knew that this somehow connected to atoms from spectroscopy. So at this time, Professor Tate was experimenting with smoke rings, and smoke rings have a stability to them that persists. So they began to think that maybe vortex atoms is a way to explain material, and they began to study knot theories. The simplest, just a ring would be a model for hydrogen. A trefoil of locked rings would be a model for the next atom, and so on. Build a theory of the atoms known then, the periodic table, by vortex atoms. And it's very compelling because it connects electricity and magnetism with materials, but it turned out to be completely different. Completely wrong from what we eventually discovered was the real structure of atoms.
Interesting. So basically, your atoms would be more like a pretzel, depending or some other
complicated pretzels, and they discovered up to 10 different complicated knots.
And it was all completely wrong. And of course, this is sort of what you're thinking about with modern string theory, right?
Yeah, it was completely wrong until we get into the realm of condensed matter physics, where there are phenomenology called magnetic skyrmions that, guess what, they behave just like vortex atoms.
Okay. So at least they got that going for them. So even though they weren't completely wrong, they still have a consolation prize. And actually, there's a hyperlink where our readers can read all about magnetic skyrmion. Well, of course, you just go to Google, or if you don't want to use Google for some reason, if you can go to what's another search engine?
Right.
DuckDuckGo, I think. Something like that. Is that right? Anyways, look up magnetic skyrmions. They're quite interesting. So, yeah, and then that brings us to today's potential blunders. No, I had mentioned one of my favorite educators, Brian Greene. He had a special on PBS, I think, over 10 years ago, called The Elegant Universe. It started as a book, and then it was made into a show on PBS. And in that show, he talked about his hope that the experiments performed at the Large Hadron Collider would validate string theory. He was looking for supersymmetry, actually. All string theorists were. And unfortunately, we haven't found any evidence whatsoever in all the experiments at the Large Hadron Collider that support supersymmetry and therefore string theory itself, alas.
Right, and some people are thinking that may be signaling the end of physics, in the sense that for a long time we've been able to predict particles that should be there. We build the accelerators that have sufficient energy to test at that level. And in fact, the Large Hadron Collider was built to detect the final particle of the standard model, which was the Higgs boson, and sure enough, they found it. The problem is they didn't find enough evidence, or any evidence whatsoever, of supersymmetry, which would be a continuation of physics that could clear up a lot of problems. One of them is called the hierarchy problem. And so if there's no string theory, it bodes very bad for string. If there's no supersymmetry theory, it bodes very bad for string theory, because string theory is dependent on supersymmetry. So we don't know how to explain our universe. That's partly what's leading to multiverse theory, which is the idea that we particularly have a very fine-tuned universe, but it's okay if the parameters are explored randomly and there's lots of universes and we're just in one of them. That's a really bad end to physics.
Wow, the end of it. That sounds eerie. I mean, really, that's literally wow. Goodness,
I
that's
don't know where to go from here.
yeah, and then so then you pivot and you talk about multi-universes.
We may build larger accelerators and find nothing more but verification of the standard model again.
Wow, interesting. There will be an interesting episode someday we might get into is what exactly how do we know that the standard model is not the definitive model? You know what I mean? Like there are still things.
It suffers many problems and it does not combine itself with gravity. It suffers many problems with infinities, in fact. So we know it's not complete.
Yeah. Interesting. How about that? Wow. Alrighty. So in future episodes, we're going to get into the next section, including the first death of mathematics, where we'll talk about Fourier, Cauchy, Dirichlet. Is that how you say it?
Yes.
Yeah, awesome. Riemann, Henkel, Cantor, Hilbert, Gödel, and Turing. The paper's available right now if you go to the website, so you can get a preview of this before our next episode. This is all for today's episode. This was a lot of fun. I am thrilled with it. It gives us so much to think about and so much to talk about. Before we go, I'd like to talk about how you guys can reach out to us. You can send us an email at turingrabbitholespodcast@gmail.com. That's TURING, as in Alan Turing. TURINGRABBITHOLES podcast. I'm not going to spell that out for you. At gmail.com. You can also shoot us an email on Facebook, facebook.com/turingrabbitholes. Also, I might make us a Twitter. I haven't done Twitter yet. So yeah, just send us an email and check out the website where you can see all of our papers and other papers. One more thing I'd like to say before we go. In addition to many papers about physics and mathematics, Alex here has written a 3-part science fiction / historical fiction trilogy. I want to plug it real quick because it ties into a lot of these ideas, a lot of the ideas that Alex has read about in physics and math and in artificial intelligence. Do you want to quickly talk about the...
Sure. Okay. It was started off from a silly dream I had in 2004, and it was the idea that people should learn history of science and history of the world from right after World War II, from the German point of view, from several characters that end up, I'm being very quick here, one ends up as a Russian nuclear weapons designer, the other one ends up developing the rockets here as part of the German scientists who came to America. And it's an exploration that, things might repeat themselves, and in some ways nationalism is rising again. So it was kind of apt. I spent 14 years writing on it. It was also to begin to explore hard science future. Might we upload? Might we make general artificial intelligence? And get into that in an entertaining way. What are the boundary conditions and how the world might split into a utopia or a dystopia depending on our politics, and ultimate conditions of life. So it's a historical science fiction turning into historical fiction turning into historical science fiction. To cover the science and also the ethics of who we are. Awesome. So that excites me because not only in your trilogy, but also on this podcast, we're going to talk about math and physics, but also philosophy, political science. We're going to talk about trends in politics, including things like the rise of nationalism and ideologies across the spectrum, conservative ideologies or liberal ideologies, and just things from an empirical political science standpoint. And, hopefully it'll help us reflect on who we are today and where we're going and what we see in the world today. So with that end, one thing I forgot to mention, I am setting up a Discord server for the Turing Rabbit Holes podcast. So if you want to chat with us, if we're on during those times, check out the Turing Rabbit Holes podcast on Discord. Without further ado, I think that's a wrap for our first episode. All right. Well, thank you.
Excellent. Thank you. It's been a pleasure.